Hello everyone. Today we're going to be solving the Ethernaut's elliptic token challenge. Now this problem requires some prior knowledge about elliptic curves. So in this video, in the description of this video, I'm going to put some links for some lectures if you're unfamiliar with this material, which is going to make this problem a little bit easier to solve. But let's just get right into it. So we have Bob created and owns a new ERC20 token. It has a voucher redemption system, and Bob can create vouchers off-chain that can be redeemed on-chain. We're told that he's a lazy developer and optimize some steps. We need to find a flaw, and our goal is to steal tokens that Alice just redeemed. And then they mentioned this Wikipedia article, which describes the elliptic curve digital signature algorithm. So let's take a look at the contract. So it's an ERC20. We have a mapping of used hashes, and we have two functions, the redeem voucher function and the permit function. They're both external and accessible. And the redeem voucher basically computes a voucher hash with these three inputs, and then makes sure that this hash has not already been used. And then with this hash, it verifies the owner's signature and it verifies the receiver's signature. Make sure the owner is the owner and the receiver is the receiver. And if everything passes, we update used hashes and we mint tokens. Now the permit function does something similar. We are receiving amount, spender, and two signatures, one for owner and one for spender. We compute a permit hash. We make sure that it's not used, and also that the bytes amount is not used. And then we verify token owner signature, but we verify it with the bytes amount instead of the permit hash. Then we also similarly verify we compute the permit accept hash with these arguments, and we verify that the spender correctly signed the signature. And if everything passes, we update used hashes and we approve token spending. So you probably already noticed that the vulnerability lies in here, where we call ECDSA recover about 4 times in this code, and we're always passing in a hash, except here. Here we're not passing in a hash, we're passing in the raw byte amount. And usually you would pass in the permit hash instead of the bytes amount. And this, this is what causes the vulnerability here, as we will see. So basically, the way these hashes work is that given a public key, you can always forge a signature for that public key. The problem is the forged signature will match a certain message that you have no control over. And usually the way you protect against that is that the code requires the message to be hashed or to be of a certain format, which is not the case here. So here they forgot to pass in the hash and they passed in the raw bytes amount, and this is the vulnerability that they will exploit. By the way, the Wikipedia article, which I suggest you read before, in its entirety before solving the problem, also mentions the public key recovery that given a message M and Alice's signature R and S, we can recover Alice's public key, which is what we're going to do. So let's actually switch and go to Remix and start implementing the solution to this problem. So I'm just going to get a new contract. So let's see contracts, and I'm going to write a new contract called elliptic token.sol. And I'm just going to paste everything from here. So there we go. Now I need to, I believe I need to adjust my compiler version. So let's just put it to 28. And I will need to update these import statements. So let me just go and get the GitHub ERC20 from OpenZeppelin. And I'm just going to get the contracts. Let me just see. Yeah, I'm just going to get the contracts here. And instead of this, I'm just going to paste the real link. And there we go, and this should be working. And this now, let me see what it does. So yeah, we need to pass in some more arguments, mainly because we're inheriting ownable. Ownable has to be initialized in the constructor. So I'm just gonna write ownable message.sender so that our contract can compile. So I'm just gonna compile it, and I'm going to deploy it on this, not deploy it, but I'm gonna check it out on the Sepolia testnet. I'm gonna get my instance address, and I'm going to paste it here, click on add address, and we will see, first of all, let me see what's happening. Yeah, there we go. So the owner is Bob, and that's fine. Total supply is this number. Let's see how many tokens does Alice have. So Alice is over here, and we need balance of. So Alice has a total supply of tokens. And also, I am assuming that I don't have any allowance. So if owner is Alice and I am the spender, I am assuming I don't have any allowance, but I'm just going to check to be sure. So yeah, it's 0. And basically, the strategy here is that we're going to call this permit function. And with this permit function, we will approve ourselves to spend a certain amount of tokens, which is greater than the number that we see here. And I'm actually going to start writing some of this stuff down. So I'm going to write another contract, which I'm going to call attack, which is just going to be a helper contract that we're going to use. And here, I'm going to have a constructor. And in here, let's just declare a uint 256 token amount. So this is the amount that we have to steal ultimately. We will also, let's declare some addresses. So let's do address Alice is equal to something, and address player also needs to be equal to something. So the player will just get it from here. This is our address, the address of the attacker. And Alice will be here. So here we go. And so the first step is that, of course, we need to derive Alice's public key, but we need to get it. In order to do that, we need her signature. So we need to get Alice's signature that she passed into this function. So the problem tells me that she just redeemed some tokens. So I assume that this function was called, and she passed in her signature, and she also passed in these parameters, which are the message. So I need to compute this message, and I need to check out her signature. So that's what we need to do. So let me just get this particular amount in the constructor. I don't think we're not going to be able to compute it just yet because we have the amount, which is the token amount. I'm assuming. I mean, I'm not sure, but I'm pretty sure it's the token amount. A receiver is Alice, but the salt we actually need to verify what it is on chain. And I'm just gonna, yeah, I'm not gonna do it. I'm just gonna comment it out for now. But what we do need is that we need the function signature. And I'm going to simply declare it here. So bytes memory function signature. And this is going to be abi.encode with signature. And what it's going to be is basically going to be this redeem voucher function. So yeah, I'm just going to, I think I'm going to write it manually for now. So we need to pass it as a string. And so what are we passing? So we have uint 256, address bytes 32, uint 256, address bytes 32, and then bytes. So this should be correct. And of course, here we cannot have memory. I do want to have it public. So there we go. This should be fine for now. So I'm just going to compile it. compile the contract, and I'm going to switch from Sepolia to just a regular Remix VM. And I'm going to deploy the attack contract and see the function signature, and see that the function signature is BEB3. And now I'm ready to get my instance address and head on over to Etherscan. So sepolia.etherscan. And for some reason, it's not being found. IO. Yeah, not sure what happened there. So let's go and see. We have some internal transaction here. We're going to click on it, and we're going to click internal transactions here. We're going to enable advanced mode, and let's start analyzing some of these internal calls. And after a quick inspection, we see that this is our function call that we are interested in. So I'm just going to copy this blob into Remix, and we're going to pass it here, and we will analyze this blob. So the first 4 bytes are the signature, so we don't really care. And then we need to separate into 32 bytes. So let's just compute 12 bytes from here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because an address is 20 bytes, and we saw Alice over there. And so we're just gonna separate into 32 byte words. Here we go, here we go. Right. And so this is actually the amount. This will be Alice, the address, and this will be the salt. So the salt, and we're going to need the salt. I believe we needed it here, and this is going to be bytes 32. There we go. And then based on that, we're going to be able to compute the voucher hash as a salt. And I actually want this voucher hash to be a public variable of my contract. I want to be able to consult this public. So there we go. Now it'll be an accessible variable. So we have Alice's message, and now where is the signature? Well, we see that the signature is actually the last argument. The receiver, Alice was the receiver in this function, so it's the receiver's signatures that we're interested in, not the owner's. So it's the last one, and we see that it's basically here. It's this one, and I'm just gonna put it here, and I'm gonna call it bytes memory Alice signature is equal to, we need to put in a hex and just copy paste everything. We need to do this, and we need to do this, and we need to remove the zeros because it's no longer packed. So we have Alice's signature, and let's just verify that this compiles. So we just require ecdsa.recover voucher hash Alice signature, and we require that it is Alice. So here we just want to make sure that we computed, like we took the correct signature off chain and we took the correct message on chain. So let's just deploy our attack contract and see. Well, actually, we already know because the constructor ran and we know that everything compiled. So we know that we have the correct signature from Alice. All right, so now what do we want is that we want to compute Alice's public key, and we need to do it off chain using VM. So let me just open a terminal, and I'm going to make a new directory called Elliptic token, and I'm going to open a new VS Code window in that folder. I'm going to open a new terminal here, and we're going to initialize a new node project. I'm going to use PNPM as my node package manager. I'm going to run init. There we go. And I'm going to add TypeScript. So these are the dependencies I need for TypeScript. I'm going to add VM and .env for our private key later on, because we're going to be needing to sign something ourselves. And we're going to also add this library for our elliptic curve operations. So we're going to need some operations with elliptic curves. So there we go. I need to now initialize TypeScript by doing this command, exec_tscinit. I'm right away going to make a small change here under verbatim module syntax. I'm going to set that to false. And under package.json, I'm just going to add a quick script, ECDSA. You don't have to do this, but I do like to have that ts node ECDSA.TypeScript, which is this is going to be my file where I'm going to be doing everything. So let's just see if everything works. Oops, that's not what I wanted to do. I want to simply npm run ECDSA. And there we go, we have hello, so everything is running smoothly. So let's compute Alice's public key. And how are we going to do that? Well, we have a very nice function, recover public key, that is provided to us by VM, and it takes in as parameters a hash and a signature, which we already have. So let's just get them from Remix. And I believe, yeah, so voucher hash is going to be our hash. Let's just go ahead and copy paste it here. And the signature is going to be Alice's signature right here. And we will need to prepend it with 0x. Now this is an asynchronous function, so we're going to need to declare a function. So async function get pub key, and we're just going to paste it here. And Alice pub key equals await. And here we just console log Alice pub key. And here we just run the function. And let's see if everything works. And indeed, we have Alice's public key computed here. So everything is good. I'm just going to paste it. And I'm going to write Alice pub key. So it's very good so far. We have the public key, and so what is the next step? Now we need to forge, based on this public key, we need to forge a signature. And how do we do that? So let's just analyze a little bit the Wikipedia article. Basically, usually what we have is that we are passed in, when we're trying to verify the signature in this step, we get these Z, we get S, and we get R, and based on these values, we compute a U1 and U2, and we then, using U1 and U2, we make this computation, which gives us some point on the elliptic curve, and we make sure that the X coordinate of that point is equal to R. So this is the main step of the verification. Now, how are we going to forge that? Is that we are going to basically do the opposite in some sense. So we are going to generate a random U1 and U2. So U1 and U2 can be anything. And based on these random values, we are going to make this computation, which will give us an X coordinate, which will give us an R. And now having R, we're going to be able to compute S from this equation, because U2 is also going to be known. And then knowing R and S, we're going to be able to compute Z, since Z will simply be equal to U1 multiplied by S. Yeah, that's basically what we're going to do. So let's just go ahead and do it. So we'll just do const u1 is equal to some random number, doesn't matter. U2 is equal to also a random number. Just make sure they're big ints. And then we will, so the first step was to make some computations. Now let's just declare some constants that we're going to use throughout. So we need a generator point. We need Alice's public key as a point and not just a string. And we're also going to need the value n, which is just going to be an integer. It's going to be a big int of something. So we're going to get that right now. But the generator point we can get as a point. So this noble sec p to 56 give us a point object, and this point object has a base property, which is the generator point. The point object also give us a from hex method, which will give us Alice's public key as a point and not as a string. And here we need to ignore the 0x in front. So I'm just going to take this and I'm going to get this. And finally, the integer. Now there are many ways to get it. I'm actually going to go ahead and get it from OpenZeppelin, the ECDSA contract of OpenZeppelin. I believe it has it. So if we scroll down a little bit and we head to the comments, we see that it is actually here. So we're going to copy paste it into our code. So there we go. And now we're ready to do some computations. So remember that the computation that we're doing is u1 times g plus u2 times q. So let's just do that. So u1 times g, that's going to be g dot multiply u1. And then to this point, we're going to add another point where we need to use the add method. And what are we adding? Well, we're adding the point q, but not just q, but q multiplied by u2. And this is going to give us two coordinates. It's going to give us a point, and we actually need both coordinates. So to get both coordinates, I'm going to call the toAffine method, and I'm going to get the coordinates as x and y. So there we go. And we have r is going to be equal to x, but not just x, but x modulo n. If we remember correctly, yeah, so the verification step requires r to be equal to x modulo n, and this is basically the forging. Like here, we're defining r to be that. So there we go. Now we need to compute s, and this is where things get a little bit tricky because to compute s, we need to basically do r. If you do a little bit of algebra and bring s to the left and u2 to the right, so we're going to have s is equal to r times u2 minus 1, or basically s is equal to r divided by u2. And so we need to compute the inverse of u2 modulo n, and for that we're going to use the extended Euclidean algorithm. So you can skip at this point of the video if you don't want to see the derivation of the extended Euclidean algorithm, but I like to do it anyway since it's good practice, and if you've never seen it before, it might be useful. So basically, the regular Euclidean algorithm is just when you find the greatest common divisor, the GCD, of two numbers, let's say a and b. They're both big ints, and we return a big int as well. So GCD, yeah, and we're gonna return, let's say, return a. So basically, the way this algorithm works is that we have a while loop. And we are going to do while b is not 0. And we're going to assume that b is the smaller one of the two numbers because that's basically where the algorithm makes sense. So we're going to be doing A modulo B, and that only makes sense when A is the bigger one. And they're going to be switching, so A and B is going to be basically B will become our new A, and our B will be the remainder A modulo B. And I'm not sure what big int, A big int, B big int. Anyway, it doesn't matter. So we return A. Oh, okay, of course it's because it's, yeah, okay. Yeah, so there we go. Now, how do we actually do the extended Euclidean algorithm? So it stems from this equation, and the equation is basically A times B, oh sorry, A times X plus B times Y is equal to some remainder R, where X and Y are just some numbers, and R is usually going to be the remainder. So if you imagine R equal to 1, and B is a prime number, then X is going to be the inverse of A modulo that prime number. So this is why the extended Euclidean algorithm is useful. So in particular, we can have an initial condition. So we can take this base equation and we can let R is equal to A. And just to emphasize it, we can say X and Y are functions of R. So A and B do not depend on R. They're kind of fixed, so to speak, even though in the algorithm they change. But for each R, we need to compute a new X and Y so that this equation holds. And we can let R equals A. And sorry, I'm just going to copy this version. If we let R equals A, our equation will become, yeah, I don't know why I can't copy today. So we will let this be equal to A, and this will hold trivially if X of A is equal to 1 and Y of A is equal to 0. Similarly, if we let R equals B, our equation will become something like this. So replace R's by B's, and this will hold trivially when X of B is equal to 0 and Y of B is equal to 1. And we can initialize this. So we can declare actual variables, XA, which will be equal to 1, YA, which is equal to 0, and XB, which is equal to 0, and YB is equal to 1. And now here I will write this modulo a little bit differently. We'll have a constant quotient Q, which is just equal to A over B, integer division of A over B, and we're just going to rewrite it as, instead of A modulo B, A minus Q times B, which is exactly the same thing. This is basically our new R, right? A minus QB. This is our new remainder that we can call R. And we can actually rewrite this remainder where we replace A by this expression. And it's going to be equal to minus Q, this minus Q times, and we replace B by this expression. And furthermore, we're just going to, we want to obtain an equation of this form. So we're just going to factor out A's, and we're going to factor out B's. So multiplied. And when we do that, it's going to be X of A minus Q times X of B plus B times Y of A minus Q times Y of B. And this is basically, as we're going through this while loop and we're doing this algorithm, this is going to give us new values of X and Y's for each new R in this equation. So I hope you follow that more or less. I mean, I'm going to link perhaps some material in the description if you want to understand the extended Euclidean algorithm in a bit more detail. But basically here, we're just going to do xa, ya, xb, yb. So how will these be updated? So the a's will become the b's. So this is just going to be xb, yb. And then the new b's will be our newly computed r's. So we're going to have, instead of x's, we're going to have xa minus q times xb. And we're going to have ya minus q times yb. And actually, if you look a little bit more closely, well, what we're looking for really is x's. We don't really care about y's because x is going to hold our inverse. So we're going to return x here, and we don't actually need the y's because x's and y's are independent. So we can completely remove the y's from the algorithm. And it's going to make the code a little bit shorter. So there we go. And one last thing we want to do is that sometimes this xa is going to be negative, and we don't necessarily want that. So we're going to check if it's negative. And if it is, we're going to add the kind of quote-unquote modulo p. And otherwise, we're just going to return xa. And p is just going to be the initial value of b. So we can just declare it here. And that's it. This is the final algorithm. So we're also going to rename this to find inverse, just so that it's clear, because that's what we're doing here. We're finding the inverse. And this is the Euclidean algorithm. Again, I wanted to go through a little bit of derivation there because this code by itself is a little bit confusing, and might be a little bit difficult to understand why this actually computes the inverse without any explanation. So let's continue here, and let's compute s. So const s is equal to r multiply find inverse of u2 and n. And this, of course, at the end, we always need to do everything modulo n. So we have our s, and next we need to compute our z. And actually, before, yeah, let's do z. And z will be u1 multiplied by s, multiplied by s modulo n. And finally, let's do v for the parity. Now, initially, v is defined as our y-coordinate modulo 2. However, because in Ethereum we require it to be in the lower part of n, we need to check that. So if s is strictly greater than n over 2, we need to switch it. So we need to switch n to be in the lower half of n, and of course it cannot be a constant. And we also need to adjust our parity v. And how do we adjust parity? Well, we just add 1, but we need to keep it modulo 2 always. So there we go, we adjust the parity. And at the end, because Ethereum always needs a v to be either 27 or 28, we're just going to add 27 to make it compatible with Ethereum. And so that should be pretty good. So let us just console log out these numbers. So I'm just going to console log. First of all, let's get our number z, which is the message. And then let's get the signature. Our signature is going to be R, S, and V. And V. And this is going to be our forged document, so to speak. So I'm just going to clear and run this function. And yeah, there we go. This is the public key. I should not be logging it anymore. So let's just maybe remove this and run this again. So there we go. So this number is our amount. So let's just copy paste it into Remix. And we're going to have a uint 256 amount is going to be equal to this number. So this is our message. This is our document, and our signature. I kept it as simply integers. And actually, let's just do uint 256. Actually, no, sorry, what am I doing? It's bytes memory forged signature, or forged owner signature. And we are going to encode it. So we're going to do ABI dot encode. And the first number is going to have to be, yeah, so each of those, the way the signatures works is that the first number has to be a uint 256. The second number also has to be a uint 256. So R and S both have to be that, and the V has to be simply a uint of 8, so only 1 byte. And I'm just going to paste these values here. So this is our R. And let's just do it on different lines, just so that it's very, very clear. Here we go. Let's get this one. And this is just 27. 27. So this should give us the correct signature. And let us just verify that this signature is correct. So we're going to have a similar statement as here. So basically, our message is going to be bytes 32 of amount, and our signature is going to be Alice's forged signature, which again should resolve, if we did the forgery correctly, it should resolve to Alice. So let's just see if this compiles, and let's see if we're able to deploy. That means that everything went correctly. And yeah, it appears that it did not quite go as planned. And let's see, maybe if we do this instead. Yeah, okay, so I think we have to do abi.encode packed so that there's no extra zeros in the signature. But yeah, basically this will give us the correct signature. And I would actually like to be able to access it. So I will just copy this. Actually, no, I'm going to copy this entire thing. And I'm going to declare it somewhere here. And of course, it cannot be memory, but it has to be public. So we have our forged signature. We know that it's correct. Now we need to actually, if we go back to the problem, we need to actually have our own signature. And what do we need our own signature for? So it's in order to sign this permit accept hash. So let's just compute that in our remix, in our constructor. And the token owner that we want is Alice. The spender is going to be the player. And bytes 32 permit. This is again something that I want to be public. So I'm just going to copy this and declare it here and make it public. So this is the hash that we want. I'm just going to compile it. And I need to deploy. So deploying this, and this is the permit accept hash. It's this particular number, and this is the number that we need to sign off chain. So let's switch back to our VM and let's sign this thing. We don't need the console logs anymore. And we're just going to say const permit hash is equal to this. So very good. And now we're going to create a new env file. So .env. And here, I'm just going to write my private key. You should do the same. And you just paste your private key here and save the file. So once that is done, you simply go here, and we need to import .env from .env. And we need to call .env.config so that our environment variables are loaded. So now we're going to have our process.env.private key. So we should be able to have this. And what we need to do is that I think it's from private. So account key. Private key to account. Yes, so VM has this this method that is available to us. So we're just going to call it to compute our signature. And I'm just going to correct the TypeScript error here. And my account is equal to this. And I think this is also an async function. So I need to define async function get signature. And I need to await. Actually, no, this is not asynchronous. So I have my account. Yeah, I have my account, and now I'm just going to do my account.sign. And this, I think, is going to be asynchronous await. And we just need the hash, and our hash is going to be this permit hash. This is what we need to sign. And my signature. And I'm just going to console log my signature. And if we run this, we should be good to go and get a valid signature. But it appears, yeah, of course, I did not call this function. So that would be a good idea. And this is our signature. So this is our spender signature that we're just going to copy into Remix. So as usual, we're going to do spender, so bytes, memory, spender signature is equal to hex. And there we go. We have it. And we need to remove the 0x. And let's just verify that it, again, resolves correctly. So we need it to resolve to spender. So I'm just going to have a require statement here. So we need a spender signature, the permit accept hash, and it's equal to, we say spender here, but really it's not spender, it's player. So we're going to require this to pass. So let's just compile and see if when we deploy the contract, yeah, so everything is correct. So this signature is correct. And at this point, we have everything we need to complete this challenge. So I am going to, I do think, I mean, we do have everything, but I just want to get the forged owner signature, which is here. So this is these are the two signatures that we need here. And now I'm going to get back my instance address. I'm going to go here and I'm going to switch back to Sepolia. Browser extension, Sepolia, and we're going to paste the instance address here. We're going to deploy the elliptic token, and yeah, at this address. And we're going to call the permit function. So let's put all of the pieces together here. So our amount was this. Let's just paste it. Our spender is us. So it is the player. Our token owner signature is the one that we forged. So it's going to be this copy pasted here. And the spender signature, excuse me, is going to be here. And I'm just gonna write 0x and this. And we should be able to transact with this particular function. So, and it appears to be not working. So we are on Sepolia, the permit function. What's not working? Spender is us, and the amount is this amount. I probably need to refresh. Let's just get the instance address once again. So where were we? Let's just compile it. It's compiled. It's elliptic token. So let's just make sure. Yeah, this is not correct. Something is not correct. So let's just elliptic token and this address. So what's happening? Why do we no longer have an owner? Oh, we're still on Remix. Yeah, okay. So let's just switch to Sepolia. Add address. So do we have an owner? We have an owner. And let's just try to call the permit function. So in the permit function, let's just try it once again. Amount, spender is again the player. Token owner signature is the, is this right? Is this the correct signature? Yeah, it must be. So token owner signature is the one that we forged, and the spender signature is the one that we computed here that we know to be valid. And now we're doing it. So I'm not sure why it wasn't working here. I just refreshed my page. Sometimes it does happen. So we're just going to wait for the transaction to go through. And there we go. And now we should have some allowance. And I'm just going to assume that we have it. And we are now ready to call the transfer from function. So we're going to transfer from Alice. So from Alice to us, the player. And the amount is going to be the entirety of her tokens. And if we press on transact, MetaMask should tell us that we get +10. Very good. And we confirm, and everything should go through. So yeah, at this point, you basically know that your challenge has been solved. And you can just wait a few seconds for the transaction to go through. And we're going to submit the instance here. and just wait a few seconds. And there you go. So this was a pretty complicated challenge. As you saw, it had a lot of steps, but I think you can learn a lot from elliptic curve signatures and just digital signatures in general and how they work and what to avoid to do when you're verifying or implementing these systems. So I hope you got something out of this video. Thank you very much for watching, and I'll see you next time.